thank the organizers for the invitation. It's a really nice meeting. And so I'm going to talk about computer simulation of heme proteins. So I'm going to explain a little bit of the title. In the first place, I'm going to introduce for the first time in this meeting simulation, computer simulation. And so when we do computer simulation in chemistry or in biochemistry, we need really two tools, two different things. The first thing is we have to define the model. And the model is, in simple terms, the way in which we describe the interactions. And the interactions in chemistry can be described at different levels. Completely quantum description would be the best, but it's very expensive. A completely classical description can be useful for many situations. And in our group, we have been using and developing in the last years a combination of both strategies that is called QMMM. It's a mixture of a quantum description for a part of the system with a classical description for the rest. And that's really good for describing electronic structure in complex systems such as proteins. And the second tool is you have to choose in a smart way how to answer questions. And in order to do that, you can resort, for example, to molecular dynamic simulations in which you simulate the time evolution of a system. Why we work on heme proteins? Well, in the first place, as almost in all situations in science, the choice of the systems to be studied depend a lot on the history and the sociology. And so I started as a hard physical chemist, and when I arrived to Argentina after my postdoc, I started to interact with coordination chemists. And so I started to work with transition metals, and then I slowly started to move into the bio field, but I wanted to keep the rich chemistry of coordination metals. And so heme proteins are very nice from a chemical point of view because they all share the same heme moiety, but they play very, very different roles according to the protein environment. And so I'm going to show you two recent examples from our group. In the first example, I'm going to show you something regarding chemical reactivity, a chemical process carried out by a protein in which we need quantum chemistry. We are going to show results using QMMM calculations. And there are two very interesting proteins from the bio and medical point of view. One is tryptophan dioxygenase, and the other is indolamine dioxygenase. I'm going to talk a little bit later why they are so important. And the second example is an example in which we study structure and dynamics of a very well-known protein. This is a more basic problem in which we investigate how the ligands enter the protein. This is the case of myoglobin, which has something called the histidine gate. Well, I will start with this first example. The reaction that these proteins carry out is this one that you see here, is the dioxygenation of tryptophan. And so this reaction is very simple. It's the insertion of an oxygen molecule, and this carried out by the first enzyme, tryptophan dioxygenase, called TDO, that is mainly in liver. And the other enzyme that carries out the same reaction is called indolamine dioxygenase. It's very less specific. It carries out the reaction for almost all indoles, and this widespread distributed in the organism. And it has been related to cancer and also to the immune system. So there are also some drugs in clinical trials as anti-cancer drugs targeted to IDO. And so it's very interesting to be able to inhibit IDO without inhibiting TDO. And so this development of selective inhibitors is of very great interest. And so if we want to perform computer simulations, we need structures. We need starting structures. And so the ideal situation is to have an X-ray structure, a high-resolution structure. So human IDO, we have a structure. It's a monomer with 2 domains, and there is a heme group in each domain. The other protein, we don't have the human protein structure. We have a bacterial structure which is very similar to the human one, but it's a homotetramer. And so looking the proteins in this way don't look very similar. However, if you take just one domain, they are really similar, and so the fold is very similar, and so it's very interesting to see the differences because they are not so trivial. And so the interesting questions associated with these proteins and relevant for drug design is, in the first place, which one is the reaction mechanism? There were several proposals, but no one really knew the real mechanism. And also if there are differences between the 2 proteins. The other question, very relevant also for drug design, is how is the substrate stabilized in the active site? And also an interesting question for a chemist is how to explain the stereoselectivity. These proteins are much more reactive towards L-tryptophan than towards D-tryptophan. And so it's very interesting to see which is the microscopic cause of that. And of course, if you answer those questions, you have the third one answered, because which ones are the key residues in the substrate binding and catalysis is a question that is answered when you understand the mechanism and substrate stabilization. And so in order to answer those questions, we resort to almost all the computer simulation tools that are available. In the first place, we use a kind of technique that is called docking. It's a very simple idea. It's just like playing like in a kid's game in order to find the best way in which one molecule can interact with the other one, the protein with the ligand. That's good, but it's not enough because it gives you some starting point. But then you have to perform a classical molecular dynamics simulation. We use a potential, a force field to describe the interactions called AMBER, to analyze these interactions and to see the time evolution, the stability of the system. Then we can resort also to more sophisticated calculations in order to evaluate, to have some quantitative estimation of binding energies, free energies associated to binding of the ligand. And the other tool in which is a tool that we have been developing a lot in the last years, the QMMM tool, is the tool we use to perform the calculations for the chemical reactivity. When you have electrons moving and electronic reorganization, you need to resort to something with quantum mechanics included. And so in the first place, we can see that we can predict by these combinations of technique binding energies. These free energies of binding are good to understand things, but one can say that the experimental values are already known, and so this is good only just for validation, to see that we are doing things more or less in the right way. But the thing that was not known in the experiments is the way in which the ligand interactions evolve in time, the dynamics of ligand interactions. And so using classical molecular dynamics simulations, we can see which interactions are the main interactions and the time evolution of those interactions. And so, for example, we can see that in the complex in TDO, we see which ones were the amino acids involved in the interactions. For example, all these amino acids are shown to play a significant role in the ligand positioning. And with the simulation, we can also get dynamic information that, for example, is not available even if you have a high-resolution X-ray structure. We can see, for example, the time in which these interactions are present during the molecular dynamic simulations, and we see that there is one interaction between 309-254 with the tryptophan NH3+, that is present almost all the time with L-tryptophan, but is almost absent all the time for D-tryptophan. And that explains the difference in selectivity. This also prompted us to propose the experimental people, specifically the group of Seung-Ru Ye at the Albert Einstein School of Medicine in New York, to perform the real experiment, and one student of our group, Luciana Capese, went there and did the real thing and confirmed this. In IDO, the thing is much more complicated because IDO is less selective, reacts almost with anything, and that's also consistent with the fact that we found more than one conformation for docking tryptophan in the active site. We have a more flexible binding pocket. We have two conformations that are both of them stable, and that can be also be exploited for drug design, because we can, for example, think about a bulkier inhibitor that may be able to inhibit only IDO because the pocket is larger and not TDO. Well, what about the reaction? There were lots of proposals about the reaction. I'm not going to tell you all the details because it's boring, but the proposals were, have not been proven, but people tended to believe that they were true. And so we started just to calculate the same mechanism that has been proposed in the literature, and we saw that it was not feasible. And so we started again, we changed the flavor of the calculation, we changed the density functional theory functional. We made all kinds of strange things, and it didn't work. And so at the end, we found an alternative mechanism in which there was a direct attack of the oxygen to the C2 atom. And so we found a very weird intermediate. It was a ferryl intermediate, iron 4O, and an epoxide. And so the people working with us experimentally, Seung-Ru, was saying, no, that's crazy, I don't believe you. And so we tried again and again. At the end, we said, okay, that's what it comes from the calculations. We cannot do more than that. But she finally ended up with finding that the ferryl intermediate really existed, and that was the origin of a very nice work, PNAS paper, in which we combined our calculations with the experimental evidence that this intermediate really existed. This intermediate exists in other heme proteins, for example, in cytochrome P450, but nobody has said that it could exist in these dioxygenases. And then we found out also that the way in which the reaction proceeded needed the involvement of the NH3+. The NH3+ of the tryptophan was catalyzed in a kind of acid catalysis, was catalyzing the opening of the epoxide to give the final product. Well, as I said before, the mutant was expressed, purified, and measured, and we saw that we confirmed the results that the tryptophan 254 was really the key amino acid. Here you can see a different number. That's because the experiment has been performed for the human protein instead of the bacterial protein. And so the conclusion of this part of the talk is that we could characterize the active sites of both proteins, and we saw the significant differences regarding size and flexibility, and that could be helpful for designing inhibitors. And so the other thing that we could obtain with a combination of simulation and experiments was a very nice characterization of the reaction mechanism, particularly the involvement of this ferryl intermediate. Well, the second problem that I'm going to talk about is a very classical problem. It's almost in the origin of structural biology. The first proteins that have been crystallized by Perutz have been hemoglobin and myoglobin. And so the first thing that Perutz observed in the crystal structures was that there were two histidines, two key histidines. One histidine is called the histidine F8 by the position in the F helix, and this histidine is directly coordinated to the iron. The other histidine is held in place by helix E, and is a histidine located here, and this histidine E7, and Perutz saw that it was involved in oxygen stabilization. Oxygen is the real ligand, the important ligand in these proteins. And so he saw this histidine stabilizing the oxygen, because you have to remember that oxygen coordinated to an iron gets a negative charge. That's an effect that in organic chemists call p-back donation. And so this effect makes oxygen negative, and so the oxygen is able to interact through a nitrogen bond with this histidine and gets stabilized. And that's key for myoglobin and hemoglobin function. And people were saying also that this histidine was very important for ligand binding and migration. It was acting as a gate. And so you have to remember that the process of ligand binding may be thought in two steps. One step is ligand access to the active site, and this ligand access is modulated by protein dynamics. It's not really quantum. You don't need quantum mechanics, but you do need quantum mechanics if you want to describe the bond breaking. If you break the bond, you need quantum mechanics. And so you can characterize the ligand binding process by two kinetic constants, K on related to the oxygen entry and K off relating to breaking the bond and taking the ligand outside. And so regarding this histidine, you can see two nice pictures. One picture is the picture in which the histidine is pointing towards the iron, and the other is the histidine pointing outside the iron. There is experimental evidence that the histidine can exist in these two positions, and this change in position is also related to the protonation state of the histidine. The protonation state of the histidine is something really subtle, because the histidine can be singly protonated in this nitrogen, in this other nitrogen, or doubly protonated. And so we made a study changing the protonation state, seeing where the histidine wants to go, and trying to see what happens with ligand migration. This is experimental evidence. I'm not going to skip this. And so our results, our simulation results, suggest that the histidine prefers to stay outside in the conformation called out conformation when it's doubly protonated. This makes sense, because if the histidine is doubly protonated, it's going to have a very strong interaction with the solvent, and so it prefers to be outside. And if the histidine is singly protonated, the things is not so easy, but it tends to stay inside. The main conformation when the histidine is singly protonated is inside. Here you have a summary of the occupancies of the open and the closed conformation when the histidine is singly protonated in one nitrogen, in the other nitrogen, and doubly protonated. But this is not saying what happens with ligand migration. We see that the histidine can really be outside or inside, but it's not saying anything about ligand migration. What happens with ligand migration? What happens with ligand migration? So in order to understand ligand migration, we perform the computer experiment that is very nice from a theoretical point of view. If you push the ligand from inside to outside, or in the opposite way, from outside to inside, you can calculate the work you do for doing the transformation. That work can be related to the free energy change. There is an equation called Jarzynski equation. The guy is a very smart theoretical physicist that relates the works performed with the free energy change. This equation can be used in a simulation, and there is also people who use this equation in real experiments. There is the Bustamante group at Berkeley that really performed the pushing experimentally. And so we use this approach to compute the free energy profiles. And so we get something that is very surprising. We see